So, I will give a short introduction to Ricci calculus. Then I will say what Einstein metrics are within Ricci calculus. Then I will discuss Ricci flows, and the last part gives some references. So, I make some provocative statements. It's hard to imagine mathematics without differential geometry. And besides group theory, I think it's perhaps the most important instruments we have in theoretical physics. And I hope this is provocative here.
I was just thinking that the field, to define field without differential geometry is impossible.
Yes. Okay. So, and differential geometry is very much alive, as you know, over the last, and it has had enormous applications in theoretical physics up till now, and also in mathematics. The proof of Poincare conjecture couldn't have been done, as you know much better than I. Here, it couldn't have been done without differential geometry. So, and there are enough problems, open problems, so there's enough to do. And I think the possible applications of differential geometry in theoretical physics still have to be fathomed out. Some modest. Now there's a not so well known mathematical instrument closely related to differential geometry, and it's this instrument I will talk about. By physicists, it's called Ricci calculus, named after its inventor Tullio Regge in 1961. I will briefly recall some of the ways it's used, and then in the main part of my talk I will show how as a tool it can be sharpened and hopefully be used effectively. So the results are new, and they will be, we are in the process of writing it up, and I hope we will be able to submit it here.
Could be nice. Could be nice.
So the main objects of Ricci calculus are piecewise linear spaces. So I use the abbreviation P.L. For the moment, it's very intuitive. It's easy to imagine it. Take a bunch of Euclidean tetrahedra or areas and glue them together whenever they fit together. By gluing together, I mean, for example, you have two triangles, Euclidean triangles, and you can glue them together along this common edge. Yeah, the edge length has to be the same. And this can be done, you have to think of this abstractly, and you don't have to think that you can embed this in some Euclidean, in some high-dimensional Euclidean space. And Regge now observed that one can associate a curvature to such an object. And this is what I will try to explain. Here is an example to illustrate this. It shows 5 triangles. You have to imagine them that they are now in the plane here. Yeah? So these 1, 2, 3, 4, 5. Is there a pointer? So there are 5 triangles. So this, and they fit together all here along their common edges. They have the same length. And now think of this, that you pull out this red vertex, you pull it out of the plane. Yeah? Think of this, that these things are elastic bands, rubber bands, but you keep these edges, you keep in the plane. Yeah? So think of this, you just pull it out, and then you would say something has happened. So what has happened? Well, it should have some sort of curvature. I mean, that's what we're aiming at. Well, if you pull this out, you would say this thing here comes out, but there's no curvature along this thing, because you can cut this out. Think of this as some sort of a tetrahedron. You can cut this out and flatten it out without disturbing it. But here's something else. Once you have pulled it out, it must have something. It should have something like a curvature. Another way of imagining what is going on is, think of this. Once you have pulled it out, you take sandpaper and you rub it a little bit. Yeah. Then when you round it here, you see there's as a Riemann space. It will not have curvature, but here it will be concentrated. The curvature will be concentrated here, and the less you do your sandpaper here, the more the curvature will be concentrated here. So there should be a curvature here. So Ricci said, in this two-dimensional context, he said, well, what you do is you take, these are still the Euclidean triangles, you just have pulled them out, so they have an angle here, Euclidean angle. So you sum them up and you subtract this from 2 pi. This you call the deficit angle, and you divide it by 2 pi again to normalize it. Yeah? This you call the curvature at this point. Now if you sum this up, this is the total curvature of this object that you have. So assume that you have triangulated, assume now that you have triangulated a Riemann surface of genus G, and you calculate this. What do you get out? You get the usual formula that you also would get if you would have calculated the total curvature of the manifold, and you would recover the Euler characteristic or the genus or whatever you would call this. So that's the basic idea. So in 2 dimensions, that's easy. I mean, that's presumably the so this is what I've just said. Yeah? The sum of the angle at the red vertex. So what do you do in higher dimensions? Well, in higher dimensions is you again have 2 pi minus the sum of angles. These are so-called dihedral angles. So you look at the simplex at an n minus 2 simplex, any, and then you sum over this. So you have a factor of the volume. Here you have 2 pi minus a sum of dihedral angles. You look at all the n simplices that contain this n minus 2 simplex, and then you sum over them. So let me explain what the dihedral angle is. The dihedral angle can be visualized in 3 dimensions very easily, and then you can and then you will see that you can do this for higher dimensions. So let's look at, so this is now n is equal to 3, n minus 2 is equal to 1. And now let's look at this n minus 2 simplex, that's a 1 simplex, and that's common to this simplex here, to this triangle here and this triangle here, and these 2 triangles, they form an angle at this point. Yeah? And that's the dihedral angle. So in higher dimensions, you just say, I have an n minus 2 simplex, and it's common to exactly 2 n minus 1 simplices, and you think of this realized in Euclidean space somehow, and then you take the same angle. You take the normal, so to say, you take the normal, the outward normal to these n minus 1 simplices and the angle between them, and then you subtract this from pi. And then you get the dihedral angle. So that's his definition. It looks inconspicuous, but it has a lot of geometry. And I forgot to say, this thing is, of course, the volume This is the volume. Because it's a Euclidean simplex, you can calculate the volume. That's his definition. And this was hanging around. So what is Ricci calculus good for? Well, in analogy to lattice gauge theory, one can formulate lattice gravity. And this we proposed, Cheeger, Miller, and I, Jörg Fröhlich, and Rochik and Williams independently in the same year. And I gave a talk when Heisenberg Institute was established in Munich. So there's something which is, you have a total curvature, which you can think of as the Hilbert action, and then you have a volume. You simply add up the volumes of all the highest dimensional simplices that you have in this thing. So you have an action which could involve a cosmological term, yeah? So this program of lattice gravity has been pursued intensively by several groups in the last 30 years and with different aspects. So that's one. And that was originally the motivation for me to look into this, yeah, to have some sort of an analogy to lattice gauge theory. Which is
a naive question. So this tetrahedron will not be embedded in this space of the same dimensions.
No. It's just abstractly.
Live somewhere.
Yes.
And then, of course, so
I give a more
embedded in 10-dimensional space, but
no. I mean, that's an open problem. It's an open problem whether you can embed this in any. It's a Nash problem associated with this. Can you embed it isometrically into some higher dimensional space? And I give you, some people told me this question have been answered, but I tell you what the problem is. Okay, you take a simple thing.
So the simplest is just several.
Let's assume that you just have three edges and you have three vertices abstractly, yeah? But now you have the edge length of this is much bigger, is bigger than the sum of this. This you cannot embed isometrically in any Rn, yeah? But what you can do is you can subdivide this, yeah? You can subdivide it isometrically, and then you can embed it, of course, yeah? And in higher dimension, that's a hard problem. I looked at it, but someone claimed you can do this. That is, if you have a PL space and you make a superable subdivision, yes, of this space, then you can embed this. So there is an answer. So there is a PL version of the Nash-Moser theorem, yeah? But otherwise it's abstractly. So I give a little bit more abstract definition.
Excuse me. So you not necessarily embedded, but you have length.
Of course, yeah. These are the data.
Yeah.
So I give you what. So, but let me tell you before I be a bit more formal. You would ask, I mean, what has it to do with other differential geometry? Yeah, with differential geometry, and that was the program that we started on, and I had the impression you do the following. You give a compact, for simplicity, closed n-dimensional Riemannian manifold with a metric, yeah? And you consider a sufficiently fine triangulation. You triangulate this manifold. This you can do. And then you associate to the edges of this triangulation, you associate the geodesic distance. And if you do this cleverly, you can realize Euclidean simplices, the higher dimension simplices. So you can calculate the Ricci total curvature. And the statement is, so in that sense, you can build a PL space which is close to this Riemannian space. And moreover, the Ricci curvature is close to the total scalar curvature. And more precisely, by choosing finer and finer triangulations, one has convergence. Yeah? That was a big effort. It took us about 3-4 years to establish this. We had to use lots of techniques. That's a hard part. That was really tough. So there is a close analogy. It's a discrete version, yeah? In a sense, yeah? So even more holds. You can define PL analogs of Lipschitz Killing curvatures. I will not go into this. They're not used much in differential geometry, but they're there. One part is so to say, and it includes boundary curvatures, yeah? And you can prove a similar convergence to the corresponding In particular, we gave a new proof of the Chern-Gauss-Bonnet theorem using this. That means Chern-Gauss-Bonnet says you can express the Euler characteristic. I'm happy to tell this here. The Euler characteristic in terms of a curvature density. Yeah? So this is a brief review. And then we finish this and never return to this. Yeah? So now I come, where am I? No, this is wrong. I should go just a second. No, this is much. No, where am I going? What is going on? Where am I? I'm page 26. Yes.
26.
That's the total. Yeah, that's the total number. Okay, so the next motivation is are there something, new things that you can do? But the order of my manuscript is not, I should have looked at this more. Yeah, okay, no, the order is okay. So I recall, the question is, can one have some sort of analogy to Einstein spaces? Yeah, that's the program. So Einstein spaces, in the smooth case, I will always talk about compact manifolds, is that the Ricci tensor, which is a tensor of rank 2, is proportional to the metric tensor, and this k is a constant. Yeah? And whenever this holds, I call this the mean scalar curvature, but one should say this is the average scalar curvature. Yeah, let's call this the average scalar curvature. You integrate the scalar curvature of and you divide by the volume, and then this relation holds. That's a two-line argument. K is this quantity over n. Yeah, so that's necessarily case. So the question is, can one find a PL version of this? Yeah, and I recall the theory of Einstein spaces, and this is a difficult subject, and not too many examples are known. So it would be nice to have some sort of instrument also in the classical case, or additional instrument to understand this. So first I have to, you see, what do you do when you look for what do you say? An Einstein space. That actually you look at a fixed manifold, any given manifold without a Riemannian metric, and you ask, does this manifold carry an Einstein metric? Namely this relation that I wrote up. So these must be special manifolds, and people have been looking for them. There are many examples. I will give some of them. So the question is, what replaces a manifold in this PL context? Well, that's an n-dimensional pseudomanifold Kn. And pseudomanifold Kn is a finite simplicial complex with additional features, which you can look up in algebraic geometry, but it's some sort of something that you get when you triangulate a smooth manifold. That's typically what you get. n-dimensional manifold. So the candidate which replaces a Riemannian metric is a map from the set of one simplices, that's what you asked before, into R plus. These are the lengths, yeah? With the following property: for each sigma n simplex in Kn, one can build a Euclidean n simplex out of these lengths. For any sigma 1, these lengths associated to a sigma 1 whenever sigma 1 is an element of sigma n. Yeah? That's the abstract definition. So this we call a metric. Yeah? So it turns out that it's better to work with the square of the lengths. Yeah? So this is now, set is a vector, it's an ordinary vector, and R is plus sufficiently high dimension, namely the number of one simplices in Kn. So, and there is a theorem, that's in a sense the hardest part, and it's not the hardest part. The set of metrics set on Kn is an open, convex, non-empty cone in this space. Yeah, so you have sufficiently many. For example, if you give all edges, that's a typical example. If you give all edges the same length, then it's obvious that you can build higher dimensional tetrahedra out of this. Yeah. So the Ricci curvature and the volume can be viewed as functions on this thing here. They're simply functions now, yeah, on this set of metrics. So this gives rise to two vector fields on this, namely, you take the gradients of these things. This we are frech genug, we say in German, we call this a Ricci vector field. Yeah? So this is a gradient. Where does the motivation come from? Well, when you take the total scalar curvature of a manifold, and you take the variational derivative, you get essentially up to some additional terms. You get the Ricci tensor. Yeah.
Hilbert.
Yes, that's Hilbert. And if you vary the volume with respect to the metric, you get the metric tensor itself up to constant and so on. Yeah? So that's why these two vector fields are of interest. And then there is set itself. It's a tautological vector field. I mean, it's just the gradient of set. You can also write this is the gradient. This is the gradient of 1/2 the length of set squared. Yeah? And this you can call the tautological. So you have three vector fields at disposal, naturally. Yes? So, next. So this gives rise to two definitions of an Einstein matrix, and I will comment on this in a second. The first, you said that this Ricci vector field is proportional, a constant, yeah, times set. So set is a PL Einstein metric of type 1, because I have two definitions, if there is a kappa 1 such that this holds. It's of type 2 if the Ricci vector field is proportional with a constant to this gradient of the volume. So these are two different definitions. So, and then there's something that is very important. This Ricci curvature satisfies a scaling property, which is analogous to a scaling property for the usual total scalar curvature. If you change the metric by a multiple, then it scales accordingly. And that gives rise to, the second time I'm happy to mention Euler. By Euler's relation, this gives that you don't have to in order to get the scalar curvature back, you don't have to integrate, you just take the scalar product with set, and then you get this here. And similar for the volume. Very trivial. I mean, the calculations that I give now are basically very trivial. So this gives you these constants and this corresponding cases. Like just so they are calculations similar to the calculations you do when you have Einstein metrics in the smooth case. So that's in particular if Z is an Einstein metric, so is a multiple. That's obvious. So we have the following two examples. The first examples, you take the boundary of an n+1 simplex and give them all the same length. Then this is an Einstein metric of both types. And then the second is you triangulate an n torus, Tn, and let the edge lengths be the ones induced by the Euclidean metric on Tn. Yeah? Tn inherits a Euclidean metric, and these are also the examples. The things that we cannot prove yet is take a hyperbolic space, which is hyperbolic spaces are also Einstein spaces. Are there triangulations? Do they have triangulations so that we can give them a Euclidean metric? We haven't come so far yet. We are trying to ask the experts. But at least the standard examples, and this is then also flat. I mean, it's Ricci flat. This Ricci vector field vanishes identically here, but here it's not the case. I mean, you get non-zero curvature, you know? So at least we have these examples. So now I come to Ricci flows. How many minutes do I have?
15.
Yeah, I will be finished before. So there's a Ricci flow of the first type. So let me recall what the Ricci flow is in the usual context. So G dot, the metric tensor is minus 2 Ricci tensor. Yeah? This is called the unrenormalized This is not of particular interest, it seems, to the experts, but there is a version which is different and which is called the normalized Ricci flow. This is minus 2 Ricci, and then you have an additional term. Namely, you add something proportional to one of these two vector fields, and here in this case, plus 2 over n times r of g over volume of g times the metric tensor itself. Yeah? That's called. And these are the analogs. You see, since I have two choices of vector fields I can play with, here's one and here's the other, and these are the proportionality factors. And what you see is the following. Recall in the classical case, assume that you are a point of G, I mean this depends on T now, that you are at the point which is an Einstein metric, then this right-hand side vanishes. That means an Einstein metric is a stationary point for the normalized Ricci flow. Yeah? This is the same here. If this right-hand side vanishes, it says it's this at this time t, it's an Einstein metric of the first type. So this normalized Ricci flow, an Einstein metric of the first type, is a stationary point for this flow. And in the second case, a similar calculation says, that's what I wrote down, I mean, that this is a stationary, that an Einstein metric of the second class is of second type is a stationary point for this Ricci flow of type 2. Yeah? I should say the examples we have, so we have no examples where we can say there's one metric which of type 1 but not of type 2 or vice versa. That would be interesting. So we haven't been able to discern this yet. So the following result holds. The total length, which is the square of this is the fourth moment of the edge length. So this is constant under each of these flows. That is similar to what is going on here. This normalized flow has the property that it preserves the volume. That's an important point. Yeah? And this here, it does the same thing, but with the lengths replaced. So, and what I said is that the Einstein metric of type 1 or 2 is a fixed point. But most importantly is that under the Ricci flow, the curvature decreases. And there's a strict decrease as long as it's not an Einstein metric of the first type. This is a result which is, I spoke to one who has worked on this, Ecker in Berlin. He said there's in the smooth case so far, he doesn't know that there is a corresponding result. So it's always decreasing.
Does it help on Ferrari conjecture? Does it help to Perelman? No?
This I don't know. I mean, that's an interesting point. I mean, whether this is of any help. I mean, they work hard to get close to this result. Yeah. So it has, of course, something to do with the result. This is also not known since you asked the question. So assume you look at the metric. You look at in the smooth case. You look at the set. The space of metrics where the volume is always equal to 1, say. You normalize the volume. You look at the flow, you know that the flow stays in the set, yeah? And the question is an Einstein metric on this set, is an Einstein metric a minimum? Yes? Here we can only say on the set, I mean, we have, I should have taken the picture geometry here. So this is a space M, and here is the set, let's say set equal to 1. So you start moving here, yeah? And the question is, if you have a local minimum here at one point, yeah? Then there is a neighborhood, whenever you start in the neighborhood of this point, the flow will be towards this local minimum, yeah? Or if it's a maximum, it will go away from this here. So that, this is a program of trying to develop a new tool that might help in problems in differential geometry. So, as for the second flow, so recall in the first flow, this is for type 1 flow. This Ricci curvature decreases always, except at Einstein metrics. In the second case, you have to take a certain average. Yeah? You take this divided by the volume to the power m minus 2 over n. Then under the flow of type 2, this also always decreases, except at Einstein metrics of type 2. So there are lots of open problems. I just list a couple of them. Can one find more examples of PL Einstein metrics? In particular, can one construct PL Einstein in analogy to homogeneous, also that means hyperbolic spaces, yeah? You have to find a triangulation. Can one find necessary and sufficient condition for the existence of a PL Einstein metric? I forgot this. So there are some classical results which I recall in this dimension. If you are in dimension through, M is an Einstein manifold if and only if it has constant sectional curvature. Then there's a result by Berger in dimension 4. It's an Einstein. If it's an Einstein manifold, then the Euler characteristic is bigger or equal to 0. And it's 0 if and only if it's flat. And Thorpe and Hitchin prove if Mg is a compact-oriented Einstein manifold of dimension 4, then the Euler characteristic is bigger than 3/2 times the absolute value of the signature, yeah, of M. So these are some of the open problems. Yeah? Other question, can a pseudo-manifold have more than one Einstein metric apart from scaling? And the question, when is the PL Einstein metric a local minimum for the total scalar curvature on the set, normalized set? And then the Ricci flow will approach the Einstein metric. Yeah, that's what I already said. And here are some reference. This is the work in preparation. This is the first work of Ricci. This is the work that was the announcement at the Heisenberg Symposium 81. And our own paper I didn't quote here. Oh, okay, well. The long article is in CMP, and then Fröhlich made a proposal, and Rocek made a proposal. But the long paper I forgot to insert, but it's in Communications Mathematical Physics. And I think I've used up my time. Not quite, but that's all I have to say.
For questions? Well, it's written here quantum, and in Fröhlich it's functional integral and so on. So is it applied to quantization of gravity in a way?
Yes.
So naively I thought that, well, I'm not expert here, but I thought that it's kind of lattice, analog of lattice QCD.
Yes, yeah.
And then,
okay, yeah.
What is the Newton constant, and what is about regularization and so on? Well,
yes, let me tell you. So this is, of course, this relates to another work that I did with Osterwalder. Osterwalder and Seiler prove that you can do lattice gauge theories, and there's some sort of reflection positivity which allows you to go to quantum mechanics. That there's the functional integration plus reflection positivity gives you, so to say, a Hilbert space. Yeah, that's what you need, functional integration. And here, what you do is, so you have e to the minus r of c, if you want, minus kappa times volume of c. And then you have a measure here, d mu z. And the question is, what is this measure? And I've been thinking about this for a while. And there is some discussion there. How do you make this into the space of all metrics you have to make, you can make into a Riemannian manifold. Yeah? The space of all set, for example, I haven't used up my time yet, yes? So I briefly recall this. I have to start with Henon from Alexandria, which is 2,000 years ago. The question is, how do you define the volume or the area of a triangle in terms of its edge lengths? There's a formula for this. There's also a higher dimension formula. If you have a tetrahedron, how you explain how you get the volume of this. Yeah? So, and that has something to do that if you have a metric, let's assume that you only have one tetrahedron, yeah, higher dimensional tetrahedron. And you take the set of all edge lengths, abstract, you take the set of all edge lengths which form a metric. Then this is a one-to-one correspondence with a set of positive definite matrices of a certain order. Yeah? And the determinant of this matrix the square root of the determinant of this matrix is the volume of this tetrahedron. Yeah? And then you can say, well, the set of all positive definite matrices is a Riemannian space. Yeah? But it's not quite unique because it has a scale factor. Yeah? So with this tetrahedron, you have one tetrahedron, you have a non-uniqueness, which reminds one of the formal non-uniqueness of the measure if you do formal functional integration of the space of all metrics. A problem that you are well familiar with. Yeah? Now, if you glue these things to, so there's already one non-uniqueness there. But once you have this, then by gluing them together, that means that you set certain edge lengths equal. Yeah? The edge lengths of the things that you glue together, you set equal. That means you have a submanifold. Yeah? In the product manifold over these things. So that's also Riemannian manifold. Then you have to calculate the volume form of this submanifold, it's the Riemannian submanifold, and you end up with a determinant, which is a Faddeev-Popov determinant, if you wish. Yeah? And this Faddeev-Popov determinant is the thing that makes life difficult. That's a program I wanted to do with Jörg Fröhlich. I mean, it's not the only place where it makes life difficult, yeah? Okay? But I explain to you. I mean, what we're trying to do is you have to do something like reflection positivity that Osterwald and I explained in the context of Euclidean quantum field theory. And reflection is time, some sort of abstract time reflection. In the context of simplicial complexes, that would be that you have a non-trivial involutorial automorphism of the simplicial, of the pseudo-manifold that you're working with. And then you have to look at the measures, and it looks like something that Ludwig observed together with Popov, that, I mean, once you have this, you will have a Hilbert space, and then you would have transfer matrices and all these things. And what you discovered with the measures that you have, that there's only one measure which allows for a Hamiltonian formulation, right? And this, it looks like there's something similar here. The non-uniqueness, you have to pick out of this non-uniqueness family, unique families, you have to pick one measure out which does the job. And in this simple example, which is already non-trivial, you can see that not all choices do what you want. Yeah? So, but I'm working on this, but I haven't given this up. But you have to do this Faddeev-Popov determinant, you have to write in ghosts and then reflection positivity to prove it with ghosts. That means Berzin integrals. I don't know how to do this. I mean, there's some mathematics that is still missing. Yeah? And I've been thinking about this for 10 years now and with no progress. Was that enough explanation?
Well, I have heard something yet.
It's, yes?
What is concern mainly Euclidean case. If there is any chance to work with Warren's signature in somewhere.
That's what I tried to explain. What Osterwald and I did is some sort of you work in the Euclidean, and what you do there. Reflection positivity is some sort of, that's a form, if this property holds, this helps you do what people call Wick rotation, yeah?
Yes.
And so that's why we are doing this. Once we have this reflection positivity, we would have a Hilbert space. And then the shift, assume that you build, so to say, a periodic torus, I mean, in a sense of a simplicial complex, then you would have some sort of discrete translation, and you would have a discrete transfer matrix, which would give I mean, the Euclidean stuff gives you not e to the ith, which you need in quantum mechanics. You get e to the minus th. Yeah, that's a trace of the Wick rotation here. Yeah, t is going to it. Yeah, but that's the expression that one would like to head for. But this you can only get if you have a Hilbert space. Yeah, and you have this contraction semigroup.
Are there any first questions? If not, let us thank the speaker again.